Okay. Welcome to lecture 21. The topic for this and the next lecture will be polar codes. Polar codes were introduced to sort of answer Shannon's question completely. Surprisingly enough, they were discovered very, very recently. It's just about that some of the results that we're presenting today are actually less than a decade old. These are going to be answering Shannon's original question. But if you recall, we had answered most of Shannon's questions this one. So let's just recap. Let's begin by recapping what is Shannon's theorem, what have we shown so far, and what is still open, and then that will lead us to polar codes. And we should say the polar codes. The nice thing about it is it's a code that was introduced extremely recently, extremely simple code. It's actually quite surprising and shocking that this code was not noticed earlier. We'll see this. At the end of this today's lecture, we'll see the code. So let's begin by recalling Shannon's theorem. So let's recall Shannon's theorem for BSC, for the binary symmetric channel. So once again, recall the setup which we have the channel. Shannon allows for any general channel, but we will focus our attention on BSC, in which a bit, say we're going to be sending in a stream of bits in through the channel, and a bit gets flipped with probability P. So it goes unaltered as probability 1 minus P, the bit P goes, and this happens independently across bits. And what we are interested in is to come up with an encoding function. Want to come up with an encoding function that potentially takes a string say it takes a k-bit string from 0, 1 to the k, produces say encoding of x, which say lies in n bits. The Shannon potentially corrupts the string. So the Shannon adds noise. So it's EX plus some eta noise. So eta is also an n-bit string, which is 0 with probability 1 minus P and P with 1 with probability P. And so the goal in Shannon's theorem is to come up with, for every P, come up with an encoding and a decoding function. End of which it gives an x prime, and if it uses this part m called m prime, and we want to come up with E and D such that probability m is not equal to m prime, but m prime not equal to m is little o. The smallest. Huh? Yeah, it should be. This is what we want to, and what exactly to work. See the exact statement of Shannon's theorem. We prove that Shannon asked for what k and n do you have an encoding and decoding process that you can do this. And basically, Shannon had shown that the following fact: for all p in 0, 1, for all epsilon in 0 to half minus p, you're allowed to make mistakes all the way up to p, and for all sufficiently large n, really show there exists a k firstly, and this k is at least 1 minus hp of n. 1 minus h p plus epsilon n. floor of this and a delta, the delta greater than 0, such that and an encoding process which takes k-bit strings to n-bit strings, and a decoding process which takes n-bit strings to k-bit strings, and sometimes it will output bot. It says this is an invalid string. Huh?
The H N should be outside that.
The check should be right. Yeah. So that's the probability. Technically, this is for all n. Let's write it for a random n, because you can just do a union. You can just knock off all the n for which this is not true. For a random n and a random eta, probability that E of m is not equal to m is less than or equal to 2 per minus 2. That's for Shannon's theorem, which we have proven this more or less. And huh?
You have listed that.
Yeah. If EFM plus theta is not equal to m, is less than or equal to 2 per minus. So Shannon proved this. You also showed that you can't improve parameters anywhere over here. This is the best K that you can get. This is here also put an impossibility version for this. But Shannon was unsatisfactory in one sense, in the primary sense that it was unconstant. It was non-constant. Everything about Shannon's theorem was non-constructive. To come up with the code, the encoding process, the decoding process, everything was non-constructive. And then we later on saw that Forney introduced concatenation to actually fix this, and he gave a constructive version of this theorem. We saw that happen. So Forney, via concatenation, got a constructive version of Shannon's theorem. And by that, what do I mean? I mean this basically, that there are three elements over here. Forney actually shown that there's a linear code that satisfies this. Once you come up with a linear code, so the linear code, how do you specify linear code? Say the generator matrix. So firstly, Forney had to come up with the give me an n, he had to come up with the generator matrix. By the way, epsilon, delta k, and or n will be the same as question is how explicit are D, E, and Forney then came up with a generator matrix. For every n, he had to build a generator matrix, but this was a one-time. That's for every n, he had built this then, and then an encoding process, which then uses the generator process to encode. But usually, once you run the generator process, encoding is trivial. It's at best an n-square type operation. It's a matrix multiplication. We can hope to get even better. We can try to get n log n, and then you need. But the main thing is you want the decoding process. So what did Forney? This one, he showed that keys construction. By this I mean obtaining the generator matrix. So we need that to be polynomial. We need the encoding time, but this is almost always order n squared. If it's once you get a generator matrix, you know encoding time, but encoding time D, which is the decoding time. We have shown that this is poly n, this is poly n. And so it seems as if the problem is all done. The catch was when we did the discussion, we didn't care about the dependence on epsilon. In particular, the inner code, we had to do a brute force search in Fournier's construction. The inner code was basically using Shannon's non-explicit construction, but the outer code was a nice construction. We had to do that. Then the inner code, you had to do a brute force construction and the search. Even if you was its length was 1 over epsilon, that means you had to run in time 2 to the 1 order 1 over epsilon. So you actually look at Fournier's construction, we write it down explicitly what we did in class. This is how much it will be. The search for the generator matrix will take the polynomial n plus 2 to the order 1 over epsilon bar 5. The encoding will be n square, that doesn't get altered, but the decoding also incurs a time 2 to the order 1. And this goes.
And the construction can to make the polynomial term by Rosen.
Yeah.
The construction part can do the 2 power 1 by epsilon by Rosen.
No. The whole the SSL circle did not give us it did not give us to approach Shannon. To get to approach Shannon, we needed. I thought we needed
anything that approaches to GB bound.
I needed something that approaches the GB bound.
Ensemble most elements are in.
Fair enough. Okay, I agree with that. That would have put the just in the decoding in the decoding. But still, you have the decoding annoyance over here. So what we want is it's for the question of the thing that was left was the following. Dependent on epsilon.
So it's about once again about the was no.
Yeah, wasn't crap. The wasn't crap respondent possibly take it off the construction, but it still remain in the decoding. So you won't be able to get rid of the exponential in epsilon for dependence on epsilon, exponential in decoding time. In decoding time. Question. And we get a truly polynomial version of Shannon's theorem. That's the question of what we'll be asking. Today we'll be answering over today in the next lectures. Well, so this question in particular, actually, for a long while, people were just satisfied with Fournier's result. That was fine. But then the question itself was not seriously considered till as recent as more than 40 years after Shannon's was one. It was Luby, Marker, Chocolate, and Spielman who posed the question. Can we actually can we improve can we get a truly polynomial version of Shannon? 2008 was when Arikan discovered polar codes. And 2013 was in 2 independent works, one of Guruswami Jia and another is Kasani Sahi and Arpanke. 2 independent works answered it. Gave analysis offered an analysis of polar codes. That convincingly answered the Dubinus and Marcus-Shokolagy Spearman question. What we will do today in lecture will be, we will not use, by the way, the Arikan also offered an analysis and stuff, except it was not completely satisfactory. Only in 2013 we had a full clean analysis, and by now we actually know this to do this for every channel. For every binary channel, we know how to do this. We will focus our attention only on the BSC, but what we will see today is actually not an analysis, not either of these analyses, but an alternate analysis due to Gasok, Guruswami, Nakiran, Rudra, and so. So actually, Madhu, Atri, and Venkat. So see, they've been using their textbook, their draft of a book, which is what we've been using. So when they decided to write a chapter on polar codes, that's when they came up with this analysis, which is what we'll be presenting. So this analysis came while writing today. Cleaner analysis, and that's what. History of this problem. Actually, for the end of this, what will we have? We will show the following. I won't state it this way. That is, we'll state that there exists. I want to state a common theorem and all of that. Let me tell you what's going to happen. So what we will show is we will give an explicit polynomial M0. We will give at the end of all of this. We will see this. We will give there exists an explicit polynomial. For all P, there exists an explicit polynomial. N0, such that what I tell you, you tell me epsilon, how much far away you want to be from capacity, then there exists an n which lies between 1 over epsilon and n naught over 1 over epsilon. N is not too large. N is polynomially related to epsilon. K is greater than or equal to 1 minus HP of epsilon n that we want.
Since 1 minus HP is epsilon close to K.
What?
This is
that right? Yeah. And encoding and decoding things which run in time, poly in actually even better, they will actually run order n log n. And so this is what we will prove, and the failure probability is at most epsilon. So that's the same thing we'll get. We'll construct a EET in this one. It might seem this is not what we wanted. We wanted for arbitrarily large n and giving you a definitive n for which an n in this range, and say the n is not too large. So basically, I'm telling you at this point itself, the capacity is being achieved. Now you could just use this construction repeat. You could just break your input into chunks of this n, do this, and then the other seems to be as if unsatisfactory, it gets only a failure probability of epsilon, whereas the Shannon's theorem and Forney had gotten this one of 2 to the minus delta n, But this we noticed that if you do concatenation, so basically what we'll do, we'll place the input into chunks and use an outer code concatenation. You'll use outer code concatenation, use an outer code concatenation. Each inner part will actually, you'll use this instead of Shannon's here. That's what we'll do. So in Fully construction, we had an outer Rick Solomon and we had an inner of these. We'll now actually use, we will use this object instead. And if you notice that construction, actually, then the error probability is just the what is the number of blocks in which the error is more than epsilon. That will be a Chernoff one if you recall that analysis. So you can get this down, you can get exactly what Shannon got, except everything now will become constructive. So what we will prove in class is this statement, and this is good enough. If I prove this one single statement, we will be able to prove the main here. The fully constructive version of one. The reason I'm not stating this explicitly is don't want to write. I don't know how much of the proof we will finish by the end of next lecture. So it might not even be this that we finish end of next lecture. But let's go ahead. But the key thing is going to be a super explicit code. E and D are going to be n log n, and n is going to happen right at the time. If you want epsilon close to capacity, you are going to get it with n, which is just poly in 1 over epsilon. At that point itself, you have code which begins showing you epsilon close. Okay. And in fact, the code which we will construct will be a linear code. So we'll be talking of linear codes. So I spent a fair amount of today's lecture. Only at the very end of the lecture, the code will be very simple, but we'll actually introduce the code only at the very end. We will talk about what are the properties we want of this code. We'll build up all the sort of machinery, and then at the very end, we will come up with state what we want of this code. So recall, a linear code can be specified by either a generator matrix, that's a k by n, the generator matrix, or by the this is more a longish matrix because I'm multiplying on the right, or by the parity check matrix, which is more a pattern matrix, which is n minus k h and throughout this one we will use m as short form for n minus k. Okay. We wanted of the code. Now, say let's be a little more pedantic. What is the code? The code is exactly that, which is taking x to gx. What was the channel doing? The channel was potentially corrupting this. So we're going to get a gx plus eta. And we wanted to recover from this. We wanted to remove out eta from this. We wanted to recover x. Notice recovering x is the same as recovering eta. If I knew how to recover eta, I knew how to recover x. So for to turn the problem slightly around, I'm going to turn the problem. So far, this is what we wanted. I want to state it in terms of the properties of the H matrix. What do I want of the H matrix for me to be able to recover eta? So let's stare at this a little more. So notice G is a matrix which takes a k bit string to an n bit string. It's sort of an encoding. That's because you want to have noise. You want to be able to withstand noise, possible corruption. Therefore, you're adding redundancy. You're adding n minus k redundancy into the code. So generator matrix is sort of expands the message into a code word. The H right now is just a parity check. It takes an n bit string and produces n minus k bits, which are basically what the n minus k parity checks tell you. You can think of it as a compressor. It takes an n bit string and compresses it to m bits. If all these m bits were the all zeros bit, then you do know that the what was given to H is the actual code word. So now let's actually apply H on this. What are we going to get? You're just going to get H eta because it's a linear operator. When you apply H on, so what happens? Let's just ask the question. What happens? What happens if we apply H on received word g of x plus eta? The H of g of x plus eta exactly just H of eta. Now, if you are able to sort of do the, if you're able to recover x from the message, that means you can recover eta from the message, beta from the received word. That in particular, it means from H eta, you are able to recover eta. From H eta, you're able to recover eta. Notice H eta is an n-bit string. You're sort of compressing it. H eta is a compressor, it's compressing it into n bits. And I'm still saying I can recover it. Why? Because eta is not an arbitrary string of length n. It's a string which you know is 0 at a location. Most of the time it is 0. It is 0 with probability 1 minus p and 1 with probability p. It's not an r. It is not the eta is not the uniform distribution on all possible strings of length n. It's just the thing that's got from the Bernoulli p distribution. So and H is a compressor for that. And what we want is this. If you want to be able to recover from this code originally, you want that H is a good compression scheme. From H eta, you want to be able to recover. So what do I mean by a compression scheme? So I will say a compression scheme. Compression scheme. And compression scheme can be defined for any distribution. You have an arbitrary distribution over the sum of strings. You feel that the distribution there, you write so long, but you can compress it to much shorter so that when needed, you can decompress. But we will state it only for the bus because the compression scheme which we care for right now is eta distribution, which is the Bernoulli Pn distribution. So let's state it precisely only for Bernoulli Pn distribution. So I'm going to state it only for this object. So the compression scheme has two components to it, H and a D. H is going to be the, and I'm going to use the word D. D was already used previously. I'm going to use this thing. This is going to be a very similar D. The H will be, the H is going to be 0, 1 n cross m. So you're compressing n bits to m bits. It's a linear compressor scheme. It's a linear compression scheme. D is an algorithm. Which takes 0, 1 n, 0, 1 m. It takes m bits. It produces back 0, 1 n. It's n cross. N cross. It's exactly the parity checking. Yeah. And D is an algorithm. Right now, we won't say talk about efficiency. It's some process which takes an m-bit string, outputs an n-bit string, and bot with the following properties. So I will say this is a f with error. So the probability, then when I pick a z at random from the Bernoulli Pn distribution, I apply H on z. So I compress the string from a n-bit string to an m-bit string, and then I apply d on it. The probability that I don't get back z is at most. So it's a natural definition for a compression Okay, that's what I'm going to define the compression scheme to be. What I want to state now is G is a good matrix for the encoding process, if and only if H is a good compression matrix. So I want to say these are if and only if conditions. So if you want to state, I want to make the following, it's rather just an observation. Then G is a good generator matrix for BSCPN. Then the noise is coming from BSCPN. By good, I mean error is less than epsilon. If and only if H is a good compressor for the Bernoulli P n distribution. Once again, by good, I just mean the error is less than. Just actually rather an observation, but let's quickly check. We will need only one direction of it. Both directions are true. Both directions are true. We will need the fact that if it's a good compressor, it's a good generator, because we will eventually reduce our problem of trying to construct a good code to constructing a good linear compressor. So why is that? So basically, I have to give you the decoding algorithm. So once I have H, there's a natural generator matrix for it. So I give you a compression scheme to work with the. Now you need to tell me that from this, the corresponding generator scheme, you can actually recover. Why can you recover? So I have to give you a decoding algorithm. What's the encoding algorithm? Of course, is the generator matrix. The encoding is X going to GX. GX is the G accompanying this. So what is it? You're going to get as input to it some R, which is purportedly GX plus eta. That's the input. The algorithm, what should the algorithm do? It has to first apply H. So one apply H on R. To obtain HR, and that will be equal to H eta. Now you just apply the decompression scheme. Apply D on HR to obtain some eta prime. You know, with high probability, this should be eta itself. So you just go and shave this off the output R minus. It should be clear that this algorithm performs exactly as well as the decompressor performs. They are exactly the same operation. This is saying from the decompressor, you can get a good decoder. And if you stare at this long enough, you can just invert it the other way. From the decoder, you can get the decompressor. And if you stare at this a little longer, which we did not do, but we did it but if you have done any course in information theory, there's Shannon's theorem there's a noiseless compression theorem and a noisy coding theorem. That is, there are these two aspects to Shannon. He says, firstly, if the channel is not noisy, but there's a distribution on the messages, you can compress the messages. That's one theorem. And the other theorem says, if the channel is noisy, then you can expand the message to do something. And basically, this observation is telling you that those two theorems are actually equivalent theorems. If I can get the best compression, I can get the best encoder. And that's why these two things go back hand in hand with each other. And this observation makes it explicit in the context of linear codes. Okay. Usually in information theory, this is taught as two separate theorems. But once you know to make this observation, It's a trivial observation, but it's an important observation. In fact, this is one of the contributions of this work of Guruswami et al. Work. This sort of clean observation, which basically shows that these two aspects of Shannon's theorems are actually equal in ways. He doesn't talk about linear codes, but there's a linear, but Shannon also proved the same thing for linear. And I think these things, I don't know how these works for linear theorems. I don't know how these work for nonlinear codes. I'll have to check this. This is the way I written the proof is crucially uses linearity all over the place, and it's also only for BSc. It's also only for BSc. The way I why is it for BSc? Because if the channel is going to corrupt, for BSc, if you're going to change the field by adding this question mark, I do not know how the compression and all will work.
No, for any binary.
For any binary channel, it will work. For any binary channel, yeah. But not any channel over any field, it will work. If it's a corruption, symmetric channel over field, it will just work. Okay. So this trivial observation. So now what do we want? We want a compression scheme that compresses n bits. So how many bits? N minus k. What was k? K was 1 minus HP. 1 minus HP. Basically, so now HP. So what we want, our goal right now, because of this one, is to design a compression scheme, rather a linear compression scheme, for Bernoulli Pn that compresses n roughly to HP of n. Now, why HP of n? So this comes from entropy and stuff. So let's actually take a slight diversion. Let's do a short primer on information theory, entropy, conditional entropy, because we will need certain properties of it. So the next 10 minutes or so, we will sort of take a diversion, do some recall basics of entropy, conditional entropy and stuff, and come back to our problem. So I want to just make sure why is HP of n pops out. And so let's take a brief diversion. Do a primer on information. So let's begin with concept of entropy. So we'll define it quite generally. So X, some random variable or distribution. This can be defined for distribution on some finite set, say M. These can be defined for infinite sets and stuff, countably sets. We will not do it. Everything we deal with will be finite. So we're talking about some random variable on a finite set. Yeah? More precisely, what is that? That means I've given you PI. For all I in M, I've given you probability PI, which is exactly the probability X is equal to pi. I've given you this sort of thing. So in particular, Bernoulli P, the Bernoulli P distribution is in which for M is the 0, 1, just the Boolean set 0, 1, and P0 is 1 minus P, P1 is P. That's this one. So I'm specifying this. The entropy of H of X, the entropy of X is defined to be summation Pi log 1 over Pi. I in M. That's the entropy description. It's informally, this was introduced by Shannon, called Shannon's entropy. It's informally, it is the number of bits required to encode an average sample, a random sample from X. That's for why Shannon introduced it, and he used the same name entropy coming from thermodynamics. Von Neumann suggested that he actually used this name. He uses the same name entropy from thermodynamics because they mean sort of similar thing. This means in the information theoretic sense. Okay. So we will need several responses of it. Firstly, we won't prove these facts, but I'll state them without proof, but they are easy to prove. They are just this one. First, this is a non-negative quantity. Never less than 0. It's a non-negative quantity. It is h of x is greater than or equal to 0 or no matter which random variable, and h of x is 0 precisely when the random variable is a deterministic. That is, there is no probability involved. It's a deterministic random variable. That's 1. 2, h of x is always what's the largest h of x can be. It's a uniform distribution on M thing with the one that maximizes this. So log 2 M will be given that x if support of x is contained. Okay, so this will h of x can never be larger. Another thing which we will use often, it's a triviality that follows from the definition. Say f is some function from M to M, and it's a bijective function. It's a 1-1 onto mapping. Now, what is the entropy of h of f of x? H of x, because from f of x you can recover x. And so it will have the same distribution as summation pi log m. It will just be jumbled up. It will be a different set of pi. You have the set of pi's will be the same. Now, as a multi-set, it will be the same, except that it will be in a different ordering possibly. And you have to just doing that reorder. So h of x will be the triviality is never stated, but we will be using this over and over again. That's why I'm formally stating this. Huh? Yeah, because basically that's just depends on that doesn't depend on order or anything. It just depends on the multi-set of PIs. The definition of entropy over here, this definition depends only on the multi-set PI. If you have this vector of PIs, as long as that is fixed, you're going to get. And if you give me f of x and x, the only difference will be the multi-set PIs will change. Okay. So in particular, the way we will be using it is in the following. An example of this will be that UVB bits. So h of UV and h of U plus VV. These will be the same because from this pair of bits, there's a bijection that takes you to this pair of bits. The entropy of this pair and the entropy of this pair. Individually, the entropy of U and entropy of U plus V might be different, but if you look at them as a pair, h of UV and h of U plus VV will be the same because it's a bijection. There's a bijection from UV to U plus VV. Okay. Other thing that we will see is if xy is a joint. I should have mentioned this. I already talked about joint distribution. If xy is a joint. pair of random variables. You can also. So the next few definitions will actually, the example already motivated this. We'll now talk not just of a particular random variable, we'll talk about a pair of random variables, say x, y. And suppose they're actually correlated. They are it's a joint pair of random variables. One can of course consider them as a single random variable xy and talk about its entropy. So what we will, let's first do that. Let's first do that is if xy are independent. So you can define the entropy of the pair xy by just looking at the random variable of the both of them combined together as a single random variable over the support which is m1 cross m2. The supports of the two. If xy are independent, what will you observe? If you just look at the above definition, if you stare at the definition, so what does it mean xy are independent? That means for all ij, for all I in m, j in m, probability that x equals I, y equals j is equal to probability of x equals I times probability of y equals j. Or in shorthand notation, I'll say Pij is equal to Pi times Qj.
So the term Pi is log 1 by Pi. It will just divide into P1, P2 plus into log P1 into log P2.
Yeah, so the log 1 over p, so if you stare at the log 1 over pi, now pi it's going to be summation over ij, pij log 1 over pij, log 1 over pij will become log 1 over pi plus log 1 over qj, so it splits. So you have summation pij log 1 over pi plus log 1 over qj. But you can just collect all the log 1 over pi terms and just summation over ij, pij. That is, you will just realize you just get summation pi log 1 over pi plus summation qj log 1 over pj. All I'm saying is if you just do this, I'm not doing it, this will exactly turn out to be h of x plus h of y. And this effect. Dependent. In particular, how we'll be using this, we'll be using it with the x is distributed according to the Bernoulli P distribution. Then h of x is our famous, the one which we'll be using, it's HP. So now if you had x1, x2, xm, which was distributed independently according to Bernoulli P n distribution, what is this? H of x n times h of p, and this is basically the reason why the compression scheme is going to have, and that's the amount of information when x is coming from the Bernoulli distribution. The amount of entropy over here is NHP, and the compressor is basically compressing it all the way up to entropy. And you can show that if you do any smaller compression, you won't be able to retrieve it. Shannon has a corresponding impossibility theorem, but you can, that's the entropy of the Bernoulli. This is why NHP appears there. Okay, so far we talked about conditional distribution. We talked about what happens if h of x, y is, if x and y are independent. We can ask what happens if x and y are not independent, in the more general case. So this is where I define conditional entropy. So notice we can define h of x. I give you xy is a pair of, it's a joint with xy is a pair of, a joint pair of random variables. So all of these quantities are defined: h of x, h of y, from what we have seen, h of x comma y. We can define all of these three quantities. What we would like to know is how are they defined? So the way I'm going to define conditional entropy, there are two ways to do it. I'm going to define it this way, and then I'm going to define the conditional entropy of y given x. What is the extra randomness I see in y given x? We're just going to define it to be h of the joint random variable minus h of x. That's the entropy left in the joint after you remove the entropy, this one. If you stare at this using the example, using the definition, you can realize that this is exactly the following. That is, pick a random sample x according to the distribution x, and look at now the distribution y, but conditioned on x equals x. And look at the entropy of this. It's the average of this will be exactly that quantity. You can check that this, you can write on this using the definitions, and this will be exactly conditional entropy. So that's going to be conditional entropy for us. And we need some some properties of conditional entropy that also I use. One is, of course, the chain rule, which is just the property h of xy is h. So it's just the opening out, writing the conditional entropy definition the other way around. H of x plus h of y given x. We more generally use it for the n thing. H of x1 to xn is equal to h of the first, the entropy in the first, the entropy of the second given the first, the entropy of the third given the first two, and so on all the way up to the entropy of the nth given the previous case. This follows one. Other thing which I will not prove, will crucially use this, is conditioning only reduces the entropy. That if you can compare h of y given x versus h of y. These are two numbers. We notice that of course if x and y are independent, these are the same. We already by definition we have studied it. But the thing will be that conditioning always reduces. Conditioning reduces. Okay. H of y given x is always less than or equal to h of y. It's equal to h of y when they are independent. This I won't prove this again. This is a property that follows from Jensen's inequality. You open this out, you get the convexity statement.
From this definition, you have to just follow from non-negativity of entropy.
Why does it follow from non-negativity of entropy?
Because h y condition of x is
that's non-negative one. But what I want to show is that's a lower bound on this. I want an upper bound. I want to show it's an upper bound. Yeah. No, it requires one more. This one. So it is of mutual okay, of mutual interest. Yeah, it follows from non-negative. But these are the same, it's the same thing. Mutual information of the quantity is defined because of this fact, whichever way you want to find. There's a more basic notion called relative entropy, which we will not define and talk about. That's a quantity which is always non-negative, and all of these are just consequences of that.
Chain rule that where defined is not, it's basically on the ordered basis, right? Like ordered chain.
I could do this for any ordering. So this is a particular ordering I have done this. You could tell me, you could jumble the order, then it will be in that order. H of x2 plus h of, so suppose you gave me the reverse order, then it's also equal to h of xn plus h of xn minus 1 given h of xn. The chain A, all of these are true. So
Yeah, my point is if you change the orders, the interval will not be same.
they will be the same because that's just the sum will be. But the terms are also going to change. Once you change the ordering, the terms will change. The term value will change. Okay. Okay. So this was just need these basic facts from this one. I will not prove any of these, I'll just assume these. All of this will be done, what we done in the first lecture or second lecture, or if you're doing a course on information. Information, it's sort of baby information theory. The two properties which I will need are some very basic things. I might do this in the end of next lecture, I might not do this also, which let's see what I want to say. Let's look at this proposition. And both these propositions are of the following fact. Suppose the entropy, I give you a Boolean form, I give you a form, random variable, and I say its entropy is very good. Suppose its entropy was 0, then you know that the random variable the random variable takes a definite value all the time. There is no randomness in it. Now, suppose I weaken this and say, suppose the entropy is very, very low. Then what you can say is basically there is one value in the support that the random variable takes most of the time. You can show this, and this is basically what this proposition is going to say. It says the first part of it says is that x is a random variable with support n, and h of x is less than or equal to alpha for some alpha 0, 1. It's a really small value. It's not 0, but really, really small. Then what I want to claim is then there exists an x in M. Because the probability that x is not equal to x is actually also very small. You might be able to get this quantity better than alpha, but alpha will be good enough for that. This is the consequence of the definition of entropy. I'll see if I can do this, but this is just a direct consequence of the definition of entropy that we have. And you'll also have a conditional entropy version of this. There was xy, the join random variables on m cross n, and h of y given x is less than or equal to alpha for some alpha 0, 1. So what does this tell you? That means once I give you x, the entropy in y is limited. In other words, you can say that for every x, choice of x, there is the most likely value for y that I can predict. That tells you that just x. So basically, I'm going to tell you the following. That is, if you define a of x to be what? The argmax over all y's in n of the probability that y is equal to y conditioned on x is being x. That's the most likely value y will be given that x is x. All I'm claiming is if then probability that when I pick a random pair x, y, probability y is just not equal to this a of x, is doesn't equal to 1. It's just a manifestation of the previous thing. That guy says there is a guy, there is the most likely guy will, the probability the most likely x will not take the most likely guy with utmost alpha. This says over a pair of random variables, once you give me x, there is a prediction I can give you for y, such that this is difference. Both these follow easily from the definition of from just the x. From both. This one follows from the definition of entropy. This will follow from the definition of conditional entropy. This definition. I would need this. Timer. Let's get return to our. Let's return to our question. So back to it. Community compressions, linear compressions. So we need to come up with this matrix H, which is a good new compression. Let's to begin with, say we're not having a compression thing. Let's think of PS. P is in 0, 1, n cross n. Let's think of it as an invertible matrix. So in particular, that would mean that H of P and for the rest of the discussion, Z, which is n bits, Z1, Z2, Zn, will always be something which comes from the Bernoulli P. For the rest of the lecture, Z, I'll use the random variable Z to indicate this will be eventually the noise for us, but this is the string that I want to compress, and I want to compress this to Pn bits. How does the entropy? So what H of D? We already saw this to be HP times n. What is H of E of Z? This is just H of Z because this is an invertible form. So this is also HP of Z. HZ has the property. HC has the property. So I'm just drawing several of these ones. This is equal to HZ1 plus HZ2 plus HZN because these are independent. Okay. HPZ is that's no longer the case. So this is no longer true. However, you see, it's going to be a pain for me to write easy all the time. So now I'm going to use W to be equal to P. So W is also an n-bit string. It represents this rearranged thing, rearranged according to the basically the invertible matrix P. It's no longer true that HW. What we have is this is not true. This is not true. HW is not equal to HW1 plus HW2. This is not true. But of course, what we should actually write is what the chain rule uses. So let's write what the chain rule uses. We can write HW is equal to HW1 plus HW2 given 1 and so on up to HWN given W1 to Wn minus 1. I will write this as short as HWI given W less than. I'm going from 1 to. Is that okay? What's the max any one of these can be? 1. They can all be at most 1 because they are all supported on the 0, 1. They are supported on support sizes 2. Therefore, log 2 is 1. Almost 1. Therefore, this value can never be larger than n. So these values can range. Now, it could be that this permutation does the fact that the fact that some of these entropies go very close to 1, some of them are extremely tight. So if the conditional entropy becomes very close to 1, what does that mean? That means if I know this guy, then I know this very, very likely. Sorry, if it goes very close to 1, it means even if I know this guy is as random as possible. If it goes to 0, what does it mean? Knowing this guy, more or less I can get this. And in fact, what will this be? Whatever that proposition claims. That is, that proposition will tell you, given this guy, I can find out the most likely value for this, and I will output this. So let's, in particular, let's do this. Let's write down this set S. So the S is a set of guys. So I give you some parameter tau, which is going to, so tau is going to be some number between 0 and 1. Let's define S tau. This is a function of P. It depends on which P we are using. S tau is basically those i's in n for which HWI given W less than I is greater than or equal to tau. That is, they are the sort of S tau is the set of unpredictables. Okay, tau is some number. We'll have some threshold tau. Let's what I want to see is how small can this be. Let's just, you already saw HW is equal to summation I equals 1 to n HWI, W less than I. Let's break this into two parts, I in S, HWI, W less than I, plus I naught in S, HWI, W less than I. I'm going to bound both these ways. So I in S, what's an upper bound I can give for this?
Mod of this.
So with them, so one each, therefore eventually mod of S. For this, what's an upper bound I can give? Tau. I know that's how I defined it. So that's tau. So this is exactly size of S tau plus n minus size of S tau on tau. I'm going to further actually, let's go into this one. I'm going to further upper bound it by, I'm going to think of tau as a very small number. I'm just going to upper bound this by n tau. So tau will be very small. Tau will be even small, much smaller than 1 over n. It will actually be little over 1 over n. What was h of w, by the way? H of w, we saw that was around, was exactly n p of n times h of p. So S tau can never be, the S tau is always at least n times h of p minus some this n. That's the. So what we will try to do is we will try to find a matrix P. So we'll try to find a matrix P such that the number of unpredictable bits will be as tight as possible. It will be exactly this. And what we will do, so what we will do is we'll call, define P 0, 1 is an epsilon tau polarizing matrix. If size of F tau is less than or equal to HP plus epsilon times. It's not significantly larger than what that above thing should be. That would be the definition. Okay. The polarizing matrix. So P is, we call it P is this. So you have this noise vector Z, the n bit noise vector Z1, Z2, Zn. P is this vertical matrix, and you are getting hold of this W. W1 on the way up to Wn. And what is S tau? So there are some guys here. Notice HW1. Anyway, what I want to say, there are some guys here. Every now and then, there are some guys here which are extremely predictable. That is, these are the guys for which HWI given W less than I is less than tau. There is no random. There is basically, once you know the previous guys, there's absolutely, there's hardly anything left here. This is more or less, there is some randomness, but it's more or less determined. That's because Z was the Bernoulli. This is not true if Z is not the Bernoulli distribution. If Z were not the, if Z were the uniform distribution in 0, 1 to the n, this will also, each one of them will have full entropy, because otherwise they have to have 1, 1, 1, 1, 1 each. each of them. But this is what this is Z is coming to the Bernoulli P distribution. There are a few of them which are completely determined. Now, but this suggests a natural compression scheme. If they are determined, why should you ever output them? So you should output only those guesses which are still uncertain, the ones which are determined. These are exactly the ones which are. These are the ones which are not in yes. You knock them all out and just output the guys in. So if P is a polarized, if an epsilon tau polarizing matrix, there's a natural compression scheme that suggests basically just take the apply P on C and just give those bits which correspond to yes tau. So the compression scheme is just the following: the compressor input to Z, so the algorithm is apply easy output PZ restricted to yes tau. That's going to be the compressor scheme. What will be the decompressor scheme? Okay, let's be a little more this one. What's the input to it? So I'm going to say the input is fair. This one I give you a P and I tell you what is the yes, which is the this one for it, and I'm going to give you a W. And typically W is going to be, I'm going to give you I'm not using W correctly, so that we use so I'm going to give you let me write it this way. I'm giving you a W, which is just a function from S to 0, 1. So I'm not giving you a W on the entire range. W should be from N to 0, 1. I'm giving you this W. So typically W is should be equal to PZ restricted to this. That's what I wanted to be typically. Not, this is not part of the algorithm. That's what I would want it to be. Yes. And also, then I have also performance parameter. Epsilon. Basically, that's the epsilon that controls this one. And what I'm going to output, the algorithm is the most natural algorithm that you can think of. Basically, we have W only on the S bits. We have to expand it out to the other bits. What do? You use that proposition which I said. This one. That is basically for I going from 1 to N. If I is in S, then you set Wi tilde to be equal to Wi. If else, you set Wi tilde to be equal to the argmax over all possible or the two possible bits, that probability Wi equals B conditioned on W less than I equals W tilde less than. Then output.
This is for recovering the space where we just omitted.
Space where we just omitted, you just do that this one, and I claim that if and all I want to say right now, we haven't talked about the matrix and all, but what I want to say, we have the following proposition.
There should be 8 pins now, right?
There should be an explicit.
Output should be 8.
Proposition is P is an epsilon tau polarizing matrix. Then compression scheme. The error most top times n. It is probability when I pick a z from Bernoulli PM. So I'm going to give it PZ restricted to yes, and that's not equal to Z. Will be less than or equal to tau times n, and that tau times n is basically a union. Each single thing will be not be tau, and you have a union bond. It's actually tau times just n minus size of s, but I'm just going to. Okay, so this proposition should be clear from what we have.
So we want epsilon to be less than tau.
Huh? No, right now there's no epsilon and tau are independent. Epsilon is telling you how close the epsilon is controlling how good the compression scheme is. It's from HP to HP plus epsilon times n. It's telling you how good the compression is from n to bits. How far away is it from the best compression scheme? It's epsilon n bits more. It is taking epsilon n bits more than what the very best compression scheme can take. Tau is talking about the error. These are two different parameters completely.
So can we go to the bound?
Which bounds?
Before stating that yes, yes.
Yeah.
So before the first minute, so that the bound on S tau by lower bounded by that n tau terms, right? HP minus n tau. So
no, that's a lower bound. I'm saying this is an upper bound. That is, it comes as close to it. So tau and epsilon are not related at all. That's it.
Can we make it like epsilon to less than tau by 2?
Yeah, you can make it. That's only a lower bound. This can be made as, so these are two different separate things. That's showing you S tau cannot, and that's talking about S tau cannot be, you cannot make S tau smaller than HP minus tau. This is talking about I want to make it HP plus something. These are two separate things. If you're talking about epsilon can't be made small, all that says is epsilon can't be made smaller than minus tau. But I'm not even talking about going in negative. I'm only going to give it a positive. I'm going to give HP plus something. This will be the quantity. Okay. Okay, we've been waxing a lot about if we had a matrix, if we had this and all. I haven't yet come to what P that we want. So I will just introduce the thing. Super simple. So, but what is P? Question is for us. Does there exist polarizing theory? In fact, why am I using the word polarizing? It's like our times, it's going to push everything to the two extremes. Does there exist a polarizing matrix? We're going to try to find out if there's one. This is what I have to give you one. So let's start with the very basic. For n equals 2, is there a polarizing matrix? So for to form begin n equals 2. What's the polarizing matrix? So I have two bits. So Z is equal to UV. I need to output two other bits, say W1, W2. In particular, I have decided what W1 is. What should W1 be? No, it has to be. These are also bits, but there are some functions of UV. Because there are only how many? It has to be a linear function of UV. What are all the linear functions? Only U. There's 1 plus U. There's U plus this is 1. So there's only one function. There's only one actual non. This one is U plus V. So let's look at the function which takes U V. I'm going to pictorially represent it this way. I'm going to output U plus V and so in other words, this is going to be U plus V, comma V. I could have given the U also, it doesn't matter. That's And I want to say this is a bit polarized. Why does it want to say this? I want to say U and V were independent bits. No longer are U plus V and V independent bits. There is some, they have got some kind of, they're sort of got correlated with each other. But I want to say U plus V is more random than UV. So let's just look at this one example and then I wrap up for today. So suppose U and V, suppose UV were distributed according to Bernoulli 0.01. Of course, if UV were distributed according to Bernoulli half, then U plus V is also Bernoulli half. But half is not. But that's not a case in which you can recover anything. That's basically adding complete not. It's changing the message to gibberish. Here we having P is a number significantly less than half. So what will U plus V be? I want to say if you take two independent things, this is going to go slightly closer to halves than each U and V. In fact, you can check it out that this will become something like 0.0199 something, and roughly it will become Bernoulli 0.02. It's going to become a little more random. So notice that the entropy of H of U plus V's entropy is going to be larger than HU's entropy, larger than HV's entropy. So what would be the entropy of H of V given U plus V? Notice that H of U plus V and V has the same entropy as H of U plus H of V, because this is, I have not changed these are independent, therefore I could write it this way. This is just a permutation matrix applied on this. So if H of U plus V has gone up in entropy, what's happening to H of V given H of U plus V? It's gone lower than HU plus HV. Sorry, not meaning the minimum of both of them, which is the same in this case. So what happens? This operation has taken the two bits which are independent bits. It produced two other bits which are now correlated bits, but it has made one bit more random. It has higher entropy in it, and the other bit, conditional on the first one, it has made it say unconditionally, of course, it's the same entropy as before. But once you know U plus V, it has made it less random than before. So it's sort of polarizing this one. The question is, this is for two bits. Can we do this for more bits? We're going to recurse. Just recurse. For larger n, recurse. In particular, we think of n of the form 2 power t. So let's just do 4 for now. So what I will do is, suppose I have A, B, C, and D are my 4 bits. We will first get whatever I want to get, A plus C, B plus D, C, D, A plus B plus C plus D, C plus D, plus C plus D. So we're going to do this. So basically, this is what we were doing to 2 bits. Now I'm taking whatever more generally, if this is for n equals 4. Let's see what's happening after n equals 8. What I'm going to do. So I have, what do I have? I have Z1, Z2, Z3, Z4, Z5, Z6, Z7, Z8. I'm going to take 1. Last one to there. You follow what I'm doing. So you're going to apply this operation. Now, once again, you're going to now then do what are you going to have? Here you're going to have Z1 plus Z5, Z2 plus Z6, Z3 plus Z7, Z4 plus Z8, Z5, Z6, Z7, Z8. Now we're going to apply this operation. So yeah. It's operation. Okay. I'm just going to do this and then fine. So so one thing, what is this going to be? This is going to be Z1 plus Z5 plus Z3 plus Z7. Okay, I'm not going to do this. I'm going to write this down, but you follow what I'm meaning here. So in general, so Z, you write it as U comma V. These are both n bit. This is an so Z is putting in 0, 1 to the power 2 power t. This is I'm writing it as 0, 1 to the power 2 power t by 2 cross. Sorry, please. 2 power t minus 1 cross 0, 1 to power 2 power t minus 1. T of Z. This is PT of Z. This I'm going to define this. The total is just going to be PT minus 1 of U plus V. PT minus 1. That's exactly what's happening. That's probably what's happening. And the hope is what we will show eventually is this. Notice that's the entire permutation matrix, and you're going to do what we'll show is there is an S for this, so that few bits, there will be a collection of S, so that the entropy there will be all very large. The rest will all become very low entropy. And just so once we have to do two things. We'll have to first show that this matrix, this is the polarizing matrix. It pushes certain bits to be very predictable, extremely unpredictable bits, and the others are extremely very predictable bits. This is sort of polarizes the whole quantity. And then we have to show how to get this yes. Once we have all of this, then the encoding and decoding, everything is written. So what we'll show in the next lecture is this matrix is actually a polarizer.
I just want to have one question.
Yeah.
Basically, if we are looking in the dimension, so we have suppose for this a to the power 2, you are 3 actually, and we have 8 the zi's. So there are zi's vector around the
1 second. Yeah, sorry, go ahead.
So basically, we are in 2 to the power 3 dimension to the power 3.
Yeah.
and we have these CI's vectors.
Yeah.
So basically, with respect to the vector 0 origin to the 8, we're just rotating around some angles.
You can think of rotating, but this is happening in the timing view in GF2 to the power 8. So I don't know what rotation means. Rotation is it makes rotation for me. I can visualize it over the Euclidean space. This is not the Euclidean space.
No, but if you include that, you have the
No, but this is not the Euclidean space. This is not the Euclidean space. I'm talking about a non-Euclidean. I'm talking over all the P, the matrix P thing. Don't think of it as a rotation operation. It's not a rotation operation. Rotation makes sense only in Euclidean. This is the permutation. This is the bijection. It's an invertible map in GF2M, and it has the property. And even among invertible map, there are a zillion invertible maps. It's an extremely simple invertible map given by this. That's the entire map.
Is this not a random matrix polarizing?
Huh? No, we don't know if a random matrix is polarizing. The matrix is polarizing. I'll come to some questions on which matrices are polarizing and all towards the end. It's a big thing we don't know. There might be some even nicer matrices than this, which are polarizing, and we would like to understand that. We don't know how to do it. This is what Arikan came up with this notion of polarizing, and he showed that this is polarizing, and it was strongly polarizing was shown in the subsequent works, and that's what we will see. So that's the code. Yeah. The code is extremely simple and code. The whole point is to show there is some S which are completely predictable bits, just knock them off, and then the resultant will be the conditions.